Okay, so I'm going to spend this last lecture on two topics. One is an application of guide to precision medicine, looking for subgroups of the population where you have an enhanced treatment effect. And then the second part of the lecture, I'll talk about post-selection inference. That is, how do you construct confidence intervals from the nodes of a regression tree. Right. So this is an example on breast cancer. So this example also illustrates an application to a situation where the Y variable, the dependent variable, is censored. So far we've not talked about censoring, but in this example, obviously, if you talk about breast cancer, clinical trials usually, I would say maybe always cannot go on until everybody has died. So the investigator may die before all the patients die. So the trial will end at some point, and at that point, people who are still alive will have the survival time censored, so truncated, right? So we only know that that person lived up to that time point. So here's a randomized clinical trial where of breast cancer patients. The inclusion criterion for the trial is that they all must have primary node positive breast cancer. So they must have number of positive lymph nodes that is not 0. Right. So in the data, the smallest number of positive lymph nodes among the patients is 1. The highest is 51. So there's one, I think, woman who has 51 positive lymph nodes entering the trial. So the more positive lymph nodes, obviously, the worse the prognosis would be. And so the purpose of this trial is to see whether hormone therapy is helpful in helping people survive longer after breast cancer. So there are about 670, about 700 subjects. That's a sample size, and of the total sample, about 1/3 or so are uncensored. You actually observe their final survival time, and about a little bit less than 2/3 are censored. So we only know that they have lived beyond a certain time. And this is, sorry, I should not say survival time. They are not survival time really in the sense of living. They are recurrence-free survival time. So recurrence-free is a time for the cancer to come back. This is often used in drug companies as a surrogate time point, because you would like to know the total survival time, but that takes too long. So they replace it with some other variable that is highly correlated, hopefully, and that becomes their target. When does the cancer come back, right? So 299 of these people had the cancer return since the trial started. 387, the cancer hadn't returned by the time the trial ended. And the range of the survival times, so-called survival times, but these are recurrence-free survival times. So they're not really life and death kind of survival times. Time for the cancer to come back. The minimum is 8 days. So there's one patient that 8 days after they entered the trial, the cancer came back. Okay, and there is one person who, after 2,659 days, the cancer still hasn't come back. And I don't remember whether for this person that was censored or not. But so there are some people who do pretty well. Of course, about half of these people had that hormone therapy, and half of them did not, right? So the idea here is to find out whether that therapy, I think the therapy is a drug called tamoxifen. Tamoxifen is now a very standard breast cancer hormone therapeutic drug, although there are now much newer drugs that are more target specific. Anyway, the predictive variables, here are the predictive variables. The first one is hormone therapy. That's the variable of interest. We want to know, do people who get this therapy really live longer, right? Then there are other variables like the age of the patient. The youngest was 21 years old, the oldest was 80 years old at the time of entry into the trial. the size of the tumors. Okay, the minimum was smallest observed was 3 millimeters. The largest was 120 millimeters, 12 centimeters. The number of positive lymph nodes, I already mentioned that. And then there are these two receptor status, they're hormone receptor status. So there are many types of cancer, including breast cancer. And some cancers, majority of breast cancers require estrogen to grow, okay? But there are some that do not require estrogen to grow. Tamoxifen is a fake estrogen, okay? So tamoxifen is supposed to starve out cancers, the type of cancers that require estrogen. So what tamoxifen does is the following. Tamoxifen tricks the cancer cell into trying to eat it, okay? But it's not really estrogen. So it's like a crocodile trying to eat a rock, okay? So the cancer cell is a crocodile and the rock is the tamoxifen. So the cancer cell is a rock, can't swallow it, can't get it out. Then the crocodile starves to death. Right? So that's how this hormone therapy, most hormone therapies work, it's like that. So it's important to know what kind of cancer each of these patients has, right? Do they have that kind of cancer that requires this kind of hormone to grow? There are some cancers, some breast cancer, that don't require estrogen. So even if the body has no estrogen, they will still grow and multiply, right? So progesterone is another hormone. Estrogen is another hormone. So these are two hormones. They are very similar. The receptor status is like how hungry is that particular cancer that you have in your body for estrogen or for this kind of hormones, right? So the larger the value, the more dependent upon the supply of hormones for this cancers to grow. And then there's menopausal status, of course, you know, because once a woman reaches menopause, and we have an 80-year-old woman here, we have a 21-year-old woman here, you know, once you reach menopause, your hormones change in the body, right? So that's a 0-1 variable. So now, because it's a randomized trial, you don't really need to use the covariates because everything is balanced, you hope, by tossing a coin, right? So you can just look at survival times alone, just a Y variable. The Y variable is the recurrence-free survival time. And then you plot this Kaplan-Meier survival curve, the two curves. One is for those who got the therapy and one who did not. These are survival curves. And you see that's a pretty good separation. The higher the curve, the longer the time it takes for the cancer to return, right? And the red line is about the blue line. The red line is hormone therapy, okay? So based on this picture alone, you would think, yeah, that this hormone therapy is helpful, all right? But of course, because you have covariates, you want to hopefully do something better. So you fit a model. That's the usual model is a Cox proportional hazards model. So if U is a survival time, so U is not always observed. For those who are censored, you don't observe U. And suppose it has density Fu as usual, then the distribution function is just the integral, right? The survival function is just one minus that. That's why the survival curves are decreasing instead of increasing. And then the hazard rate is the instantaneous probability of death conditional that on you having survived up to that time, right? So it's density divided by the survival function. And so the Cox model, you know, David Cox, a brilliant statistician, I would think maybe in my mind is the most brilliant who have lived during my lifetime. All right, there are a lot of brilliant statisticians, but Cox that's fantastic. I mean, he has done so much. And this proportion hazards model is one of his contributions. Our tools, you know, the whole field of survival analysis will be set back much more if he had not invented this model. It's a very simple model. If you look at this model and you understand this model, you wonder if Cox had not invented it, somebody would eventually, okay? It may take a bit longer, but so he postulated the following. This is the hazard function, right? This is the probably instantaneous rate of death given U, right? So you say after 10 months, right? What is the probability that I would die if I live 10 months? That's lambda of U. That is if you don't have covariates. But if you have covariates, then you have an X, right? So then it's not just lambda of U alone. You want to model the X. Now, his brilliance is to separate out the X from the U. He made them factors. Okay, right? They could be any kind of function. Lambda is a function of two arguments, U and X, right? But his brilliance is to say that, so this is a model, right? The model is that the instantaneous rate of death, the hazard rate, is a product of some lambda zero, some lambda function, which is unknown, and times the exponential of E of X, of X of beta. X of beta is like a linear model, right? So if you take log of both sides, right, of the hazard rate, you get log of lambda zero plus just X times beta. Because the exponential, we take log is X. X times beta is exactly the kind of linear model right-hand side. Okay, so now log of lambda zero now becomes a nuisance parameter. Okay, it's like the sigma in the linear model. We are more interested in the mu's. We don't care about the sigma, right? It's a nuisance parameter. And he managed to set it up so that you don't have to estimate lambda zero. Lambda zero is a function. Beta is a constant. X are the covariates, right? So beta is a constant, but lambda zero is a function, it's a curve. So it's very hard to estimate lambda zero, but he found that if you use partial likelihood, you don't have to estimate lambda zero, okay? And that's one thing. The second thing is that if you want to interpret beta, right? In the usual linear model, we have y equals to beta 0 plus beta 1 x plus epsilon, right? So in the usual linear model, these squares, you interpret beta 1, the slope, as how much the expected value of y increases if x increases by x to x plus 1, right? You change x to x plus 1, the difference is beta. Well, with this formulation, beta, so you can see the x plus 1 here and the x, right? Okay, so beta is now a constant of what is called this is a log hazard ratio. It's a ratio of two hazard rates. It's a constant. And that constant does not depend on you. In other words, if you believe in this model, and if beta is the effect of that therapy, and if that effect is positive, some number, then you can say that this drug is good for you regardless of your age, because it's independent of you. Normally, you would think, right? You would think that if this drug is good, it's probably not good for everybody. Maybe it's good for older people. Maybe it's good for younger people. Maybe it's good for whites. Maybe it's good for non-whites, right? But with this model, so it is still a model, right? All those things disappear, okay? Right? So, so this has become a standard approach to analyzing survival data. Of course, there are people nowadays who criticize this model by saying that this model is very hard to satisfy, right? That is actually because it's very hard. There's nothing wrong. Actually, there's nothing wrong with the right-hand side to make it a product of two terms. Yes. X is a vector. Yeah. So X are all the covariates. You know, age, tumor size, and so forth. It's like a linear model kind of thing.
So in the last equation, should it be?
Oh yeah, sure. So in the last equation here, I'm assuming that only one X has one added to it. So like age, if you are interested in the effect of age. But actually in this case, if beta is a treatment effect, this X is that 0-1 hormone therapy. Okay, so when you do this thing, you have many betas, actually not one beta. A beta for age, a beta for tumor size, and a beta for hormone therapy, right? So here, this is, if beta here refers to the effect of hormone therapy, that's exactly the effect of hormone therapy, okay? So as I was saying, people now, they say that the proportional hazards model is hard to satisfy. That's because they're always looking for X beta kind of a linear model thing, right? And they don't know, they're not at interaction terms and so on. Basically, the X beta can be very flexible. In fact, X beta here can even be a spline. I mean, it could be anything, right? We're just separating the U from the X's. Okay. So, and what I'll do here is I'm going to replace X beta here with a regression tree. Okay. So then you know, how do you criticize that the proportion hazards model is too rigid? A regression tree is very flexible. Right? Okay, so now let's pretend we do the classical approach and we get this answer, right? So I highlight in yellow the treatment variable, that's hormone therapy 0, 1. And it has a negative coefficient, very significant, right? So if you're not familiar with the proportion hazards model, think of this as ordinary linear regression model, okay? So negative coefficient means that your instantaneous rate of death is less with hormone therapy. So you want it to be negative, right? You want to decrease the hazard. So age is not significant if we based on this. You know, this is not significant. Tumor grade is significant. Number of positive lymph nodes is significant. You would expect. In fact, this is super significant, 10 to the minus 11, right? I mean, if somebody has a lot, 51 positive lymph node, you know that this person has very little chance to survive, right? The whole thing has spread, okay? And progesterone receptor status is significant, right? Estrogen is not. So I remember maybe 15 years or so, maybe 20 years ago, when I first presented this result in a class in Wisconsin, there was a doctor from Taiwan. I don't know what he was doing there. He was on sabbatical. He wasn't visiting the stat department, but he was there. And when I showed this, he raised his hand. He says, "This doesn't make sense." And I said, what do you mean it doesn't make sense? He says, "I'm a doctor." That's where I'm most worried. You know, if one of you raises a hand, I talk about a medical example, you say, "I'm a doctor." He said, he's a doctor. And he says, in medicine, we know that hormone therapy is an estrogen replacement. How can estrogen be not significant? Right? I mean, estrogen is a target. It is not significant. Well, so this brings us back full circle to my initial criticism about parametric models. You cannot interpret the regression coefficients. The reason the estrogen coefficient is not significant is because progesterone receptor status, which is somewhat related, ate its lunch, right? So what you are seeing here, those regression coefficients are the after effect. For every variable, its regression coefficient is its effect on the residuals after all the other variables have, you know, expanded their power on the Y. So progesterone receptor status is still very significant because there's still something that progesterone receptor status can explain after you have used estrogen. But the reverse is not the case. And actually, if you now remove all the other variables and just regress, just use a proportional hazards model on estrogen receptor status, it's super significant. Okay, so that's a problem. This is my issue with interpreting linear models. You really should not interpret them. Okay, because if you throw away one variable, all the coefficients change. Okay, and it always annoys me when people say, when I talk about regression trees, they say regression trees are unstable. Well, you know, what do you mean unstable? They say, oh, if you take away some points, some data points, then the tree changes. Well, you take away some data points. Here, I'm talking about taking away a variable, but you can take away some data points, and you wouldn't expect those coefficients to remain the same, right? Okay, so my initial reaction to the doctor's comment is, oh, because they are correlated, right? We think they're correlated. Actually, they're not. So I plot estrogen receptor status versus progesterone receptor status. The correlation is 0.4, less than 0.4. Okay, normally you wouldn't consider that high correlation, right? They're not, no, you would think that, oh, they're maybe very highly correlated. So once estrogen receptor status in the model, you add, once progesterone receptor status in the model, you add estrogen, there's nothing much left to explain, but they're not. But after I looked this plot, I saw there's a whole bunch of data here I don't even know what's going on. There's so much ink. So I added 1 to each, and then I took logs. So you see the scale? This is logarithmic scale, okay? So that I can separate out. Guess what? The correlation went up to 0.64. It's almost double, okay? So what I did here was I just added 1 because I want to take log, and if there are a lot of zeros there, I cannot take a log of 0. So I just added 1 to every one of these x1 and x2. And then I took logs to sort of not have everything bunched near 0. And suddenly I see this correlation is 0.64. Actually, you could have gotten a similar correlation if you have used Spearman's rule, which is rank correlation. If you have converted all the data to ranks and then calculate correlation of the ranks, you get about 0.64, which makes me wonder, people who study genetic data, they have hundreds of thousands of variables, right? They do a sweep of correlations. They use Pearson correlations. How many people do other things? So if you just use Pearson correlation, you use the left, you look at it, you say they are not correlated or very badly correlated, right? So so things are actually quite complicated. But here's my question. Okay, so I go back to this picture. See, in an ordinary situation, so if from the drug company point of view, they'll be very happy if they see this picture, because then they can say they get the drug approved, all right, and they can make a lot of money. Usually in the drug company, they will have these two curves very close to each other, right? So they invest 5 years of research on it. They spend $5 billion looking for a drug. Sometimes it's more than $5 billion, sometimes more than 5 years. And they have no significant difference between the treated and untreated. What do these people in big pharma do? They don't want to say, forget it, they already put in $5 billion. Now they look for subgroups. If the red and blue lines are close to each other, might there be some subpopulation where they separate such that for the other one, separation is the other way around. So they average out, they're like no difference. If they can find that, then they can maybe get drug approved and then sell it to that market. That's called precision medicine. Okay. Of course, in precision medicine, they deal with 500,000 gene expressions. I don't have any gene expressions here. Okay. But in my example here, it's opposite. We already see proof that the treatment is effective, right? Overall, you can see it here, and you can see it here, right? Okay. But we all know that not all drugs affect every patient the same way. So if you look at this graph and you see that it seems to help on average everybody, might there be some people for which it doesn't help? If there's some people if there's a subgroup where it has no benefit, the complementary subgroup will have a bigger benefit than this graph shows, because it's an average over 2 groups, right? So here, I'm not trying to look for a subgroup where this drug is good or super good. It's already good. I'm looking for a subgroup of patients who do not benefit, who are given this drug thinking that they are benefiting, but they're dying because this drug is useless. You know what I'm saying? Okay, right? So I'm saying, is there a subgroup where this drug is not useful at all? And if we know who are these people, maybe we should give them some other treatment, not keep giving them the same thing. This is on average, yes, on average, right? But when you have the disease, it's personal. It's not, the average doesn't mean anything at all. Okay, so those are the 2 questions. Is there a subgroup where it is ineffective? And if there is, then the complementary group will be more than average. Now, in order to do this, you need to look for an interaction between the treatment and, say, age. Or treatment, if you think that age, you think that older people will benefit more and younger people don't benefit. That's an interaction effect, right? Or if you think that people with high progesterone status or high estrogen receptor status are more likely to benefit, then in your in your Cox model, your X beta, you should have a term, you should include a column X that is a product between the treatment and either progesterone receptor status or the product between treatment and age, whatever, right? You need to have that. But the model we fitted did not have that, right? They're all linear terms. I have no interactions. Okay, so let's try that, add interactions, see what happens and refit. Okay, so now I throw in instructions of every X with hormone therapy. So this was hormone therapy by itself. This is a cross product between hormone therapy and age. This is menopause and so forth. Right? None of the p-values are less than 0.05. Not even the main effect term for hormone therapy. Okay. This is further evidence that it's really risky to interpret the coefficients. When I throw in the interaction terms, hormone therapy is completely washed out. So if we had started with this model, you would say hormone therapy is useless. Right? Okay. That's what I put in highlighted in yellow. Right? The only thing that's significant left is, of course, number of positive lymph nodes is always there. I think that's a number of positive lymph nodes is, I think, an indicator of seriousness of the disease, right? I mean, that's that one. Even if you have an interaction, see, even though we have an interaction with positive lymph nodes, that one, the main effect term, is still significant. Okay, so what do? I use guide. So what guide does here is guide would fit, would split, but would fit a model on both sides. Each side, in the previous regression three examples we have seen, I fit a constant, right? Like mortality rate for COVID and so forth. Here, I fit a simple model. I fit a proportion hazard model with only the hormone therapy term. So, so here would be, I would fit in each node this model. See, guide is very flexible. You can choose whatever X variables you put in. Okay, so here, Varun, you asked about X being a vector. Here now, X is just a column, which is that 0, 1, whether you're given the treatment or not. The other X variables are used to split the tree. Okay. So it says the best split is progesterone receptor status. This number is the hazard ratio of the treated versus the untreated. Okay, so everybody together, the hazard ratio of the treated to the untreated is about 70%. So the hazard for the treated is 70% as high as the untreated. So it's, you know, the hazard of dying. That's why we see in the Kaplan-Meier curve the red and blue, right? That's a numerical summary. But once you split, so these are the group, these are the people with low progesterone receptor status. Okay, remember, high progesterone receptor status means that the cancer you have needs estrogen. The higher, the more it needs. So if progesterone receptor status is low, that means that cancer, that particular cancer cell that is growing in your body is not so dependent on estrogen. So if it's not so dependent on estrogen, you see that the hazard ratio now increases to 90%. So it's almost like no effect, right? The group for which the group of patients for which they have this kind of cancer that depends a lot on hormone, the hazard ratio now is 50%. So it's half, right? Basically, your risk of dying is half for this group of people. Okay, so this is the group of people that actually we should not be giving hormone therapy. This group is actually quite substantial, 274 versus 400. 1/3. Okay, 1/3. So that's why almost as many years ago, after I gave this talk, and that the doctor mentioned this, I gave another talk where one of my former students, a woman student, was listening, and she told me she just had breast cancer, and she was given tamoxifen post surgery. She said at the time, that's standard. Everybody post surgery after breast cancer is given this drug, but 1/3 of them, for that 1/3 is about, is it 1/3? 274 versus 400. Yeah, it's useless, and they'll die. They're basically taking this pill for nothing. Oh, guide also tells you when it finishes, it tells you what is the second best variable. So the second best is estrogen receptor status, right? So now I draw the same tree, but I now show you the two curves. Now, previously I showed you one curve for everybody. That's at the root node. Now I show you one curve for each side. And you can see now that they are twiddling each other here on this side, right? They're twiddling each other. Okay. Whereas on here, you see the separation is almost double. It doesn't look the same as before, because before I put everything in one screen. This is why I squeeze it like that. Okay. So, well, guide can actually do a lot of things. It can fit. So what I showed you is it just fit the treatment effect for Z is the treatment variable, but it can also include other X variables, so polynomials and so forth. So that's if people want to fit a proportion hazards model in each node, but they also want to include other predictors. So how do I do it? Okay. Now, there are many algorithms that claim to fit tree-structured proportion hazards models. What they do is that they split, and then within each node, they fit a Cox model, right? Now, you remember the Cox model has a lambda 0. It's called the baseline hazard rate, right? If you are lazy, and after you split, but even before you split, at each node, you fit this, you have a lambda 0 for every node. That lambda 0 is not the same anymore, which is not a proportional hazards model, right? The splits are the indicator terms. They'll go into the X beta, all right? So the lambda 0 should be constant, but all other implementations of proportion hazards regression trees just have a new lambda 0 for each node. So, but guide gets the same lambda 0. How does it get it? So I'll just quickly say this. Basically, if you look at the likelihood function for the Cox model, all right, you take a log likelihood. It has two parts. Delta is that censoring indicator, right? Delta is actually what you call the death indicator. It's 1 if the person is uncensored, 0 if it's censored, right? And so the first term is actually, it actually looks like a Poisson regression likelihood, okay? And the second term does not depend on X. And this is not my discovery. This was way back in 1980s, okay? So in other words, you can actually you can estimate the beta terms using Poisson regression instead of writing a new code for Cox proportional hazards. Because the ultimate answer, okay, can be obtained numerically by using a Poisson regression model. You have to redefine what is the Y variable. In the Cox model, the Y variable is the censored survival time. In the Poisson model, the Y are the indicators, because Poisson uses non-negative integers as a response, right? So here, our response is 0, 1, never goes beyond 1. But you know, the Cox computations, the Poisson computations, they don't know about that, right? And then the lambda 0 is like an offset variable because it comes out as a log in front when you take log. Yeah. In Poisson regression, there's a variable called offset. Usually, in Poisson regression, you want to model the log of the mean, right? Mean number of counts, for example, right? But sometimes you want to model the log of the rate. So for example, if you want to find out how bad is COVID across the United States, individual states? Well, the states have different populations. You don't just want to count how many COVID cases, because California will have a lot because the population is very big. So you want to divide the number of counts by the population. So you want to take the expected value of the log of counts divided by population size. But that becomes the log of number of counts minus log of population size. And that minus log of population can move to the right-hand side, right? It looks like another regression term, but it has coefficient fixed at 1. Normally in regression, for every x, you let the beta float. But in this thing is log at 1. That's called offset value. Okay. So if we know lambda 0, then log of lambda 0 becomes the offset, and just use regular Poisson regression. But we don't know lambda 0, so what we do is we iterate. So this is a guide algorithm. Okay, so you need a lambda 0. What I do is I just use the lambda 0 from the Kaplan-Meier estimates, the first two curves I showed you. Right, I use that as an initial thing, and then I grow a tree. After I grow a tree, I re-estimate lambda 0 from the tree. And I do it again, do it 5 times or so, right? And that allows me to have the same lambda 0 across the nodes. Okay, so, all right. So that's the first part. Unfortunately, I used so much time already. So you would think, wow, great. We managed to, oh, actually I have another graph to show. Oh, later on I'll show you. But the problem is that when I started showing this to doctors, they get excited. But then nowadays, people in medicine, they are so tuned into statistics. Every time you show them some results, they want to know the p-value. When I was a graduate student, I would attend annual meetings from, say, ASA, American Statistical Association. And at every annual meeting, there would be 1 or 2 sessions, special sessions. People give talks, how to get the rest of the world to be excited with statistics, selling statistics. Now, you don't have enough to sell. They come begging for it. They just want the p-values. So they want to know this hazard ratio, 0.5, 0.24, is it statistically significant? Is this statistically significant? Is this statistically significant? Is 21 statistically significant? Okay, and I used to tell them, well, this is all exploratory, okay? Because we don't have a model, right? So you think that this is measuring, this is something like beta hat, right? But what is beta? What is the estimate? In a linear regression, you have the model. You start with the estimates. You have the model, then you estimate, then we get beta hat. Here we don't have a model. It's non-parametric. If I get another data set, I may have no splits, or I may have more than one split. Even if I get exactly one split, it may split on estrogen receptor status. Even if it split on progesterone receptor status, it may split on 22. Right? But if you tell them this, they are not happy. They will say, well, interesting, but I'm not going to use it because it's, they want to test hypothesis. So this brings me to post-selection inference. So this is post-selection. We have selected a model, right? And we want to see how significant that is. Of course, after you select a model, you can refit the model pretending that there was no search and just get those p-values from R just on that subset, right? But that will be underestimating the variance because you're not accounting for the uncertainties involved with the search, right? So let me address that. So I have to skip. I have a lot of other examples. I'm just going to skip to. I also have one application very interesting on car collisions where the variables are angles, but I don't have time to talk about that. In an angle, if the tree splits on angle, if tree splits on edge, you have a negative to infinity or 0 to infinity line edge. Then you cut the line, you get two nodes, right? If you have an angle, you have a circle. So you have to cut a sector, like you cut out a slice of pizza. So you have two things in order to get that. So I'm going to jump to post-selection inference, right? So first of all, let me address a split point that progesterone receptor less than or equal to 21. If you ask whether that number 21 is statistically significant, you are assuming there's a jump. That you're assuming there is a beta, which is 21 or 20, and you're trying to estimate the beta, right? But in real life, there's no such jump. Everything is smooth, right? So, for example, here, or the other thing is the subgroups may not be unique. Okay, so for example, here I show you this picture. I grow two trees. One is with progesterone receptor status, and I tell guide use the second best variable, and it got me this. So now both give me two different subgroups. If I use the tree on the left, I'm cutting left and right. So this is one subgroup, and this is another subgroup for the tree on the left, right? For the tree on the right is upper half and lower half. So which is the right subgroup? Right? Is it the intersection or is it the union? All right? It really doesn't matter. If you're working for the drug companies, they want to sell drugs. To them, the union is better. Then they sell more. But if you have the group too big, then the effect is diluted because you are allowing people who may not benefit as much. They may still benefit, but not benefit as much. So if it's too diluted, they cannot get approved by the authorities. If you use the intersection, you're safer, but you sell less. Okay, but anyway, that's not a statistician's problem. Okay, that's a drug company's problem. But my point here is there's no unique subgroup. So when people ask for a subgroup, I think as long as you get some subgroup, you will really find something. Okay, that could be multiple subgroups, and some subgroups may be easier to identify because they may require some variables that are easier age, right? Then progesterone receptor status may require some drug or some blood drawn from the body or whatever, or some biopsy, right? Okay, so the split point I think is hopeless to try to ask whether it's 21 or 20 or 22. It doesn't matter, right? They're all subgroups. You increase that, your subgroup is smaller. You decrease that, the subgroup is bigger. Okay. So they're not unique. So I would keep telling people this is not unique, but the doctor will come back and tell me progesterone receptor status less than or equal to 21 is real. It refers to a real population. There are people with progesterone receptor status less than or equal to 21 in the world. Right? You may have found it by accident, but it's not an imaginary population. Right? So they want you to be, can you estimate that effect for this real population? So I can't escape that. So for 30 years, I was pushing away, so this is exploratory. So I almost have to apologize. I'm sorry, this is exploratory. I can't do it anymore. But after I started consulting the industry and find that I have to solve the problem. So here's my solution. Okay, so I'll leave this there for now. I'll tell you what my solution is. So suppose I have this tree. We'll go back to this tree. Okay, so forget about this tree, just one tree. suppose out of desperation, I want a standard error around this. I want a confidence interval, right? And I'm really desperate. So I just take the subset of 398. I ignore the fact that I used guide to find it, right? I just take that subset and run Cox proportional hazard model using R or SPSS or SAS. I just get, and they will produce you the p-values, right? So the usual confidence interval is this plus and minus 2 times the standard error, right? That's the usual sort of 95% confidence interval, okay? I know this is too short. First of all, the standard error is too short because standard error only uses the data in that node. It doesn't care about this uncertainty up there, right? So the variance involved in the search is not accounted for by standard error, okay? So the confidence interval has to be wider. One way to widen it is increase the standard error, somehow inflate it. I spent a lot of time figuring out how to inflate the standard error. I couldn't, because the standard errors they change from node to node, because they depend on the sample size. Some nodes have bigger sample sizes, so the standard errors are smaller. Some nodes have smaller sample sizes, the standard errors are bigger. And also the standard errors depend on the variable, right? In the end, I thought I'm going to make the confidence interval wider by increasing the multiplier 2. Okay, I'm going to increase it beyond 2. It has to be above 2. Increase it to what number? Okay, so what should one do? What do you think? Suppose I have the true population. Suppose I have all the cancer patients in the world who have ever lived and whoever will live. I have this whole population. I have F. All right. Then I can find out if I use 2 standard errors for every node, what is the simultaneous coverage probability? I want my confidence interval. So I want simultaneous confidence intervals, a confidence interval for the treatment effect for every node. I want to find the probability that they all cover whatever they're supposed to cover. All right. If I have F, I will know what is my estimate, because in F, I can define this population. I have this infinite population of data, right? The true data. I look at the half where projection receptor size is bigger than 21, right? And I know what is beta for that one. Okay, what I have is the beta for this sample, right? So I'm going to, if I have F, so everything right now is if I know F, I can calculate beta. I just pour it down and basically refit that node with the whole infinite population, right? And then so I have my true beta, and then I have this beta hat plus or minus 2 standard errors, right? I'll see whether it contains this estimate, right? If it contains, I say yes, I got a hit. If it doesn't contain, I say no. All right. I do this for every terminal node, and I count how many times when all my intervals contain their estimates. All right. Okay. And so each time, basically, each time I have this thing, and then I can find out that I basically have to draw from this each time I build a guide tree. I forgot to say that. All right. So I do this thought experiment where each time I have this infinite population F, I draw a random sample, same sample size as the real data. I grow a guide tree on this sample, this fixed sample. All right. And then I calculate these confidence intervals, beta hat plus or minus 2 standard errors. And for each one, I know the truth. Right. So I do this like 10,000 times. Right. And I say I got a success if at each time all the intervals cover what they're supposed to cover. Right. And suppose I do that, and the answer is, suppose I want them to cover 95% probability, simultaneous probability. Suppose it comes out 90%, which is not surprising because you know that they are too short. What will you do? You repeat it with, instead of 2 standard errors, 2.1 standard errors. You repeat it again and see now the coverage will go above 90%, maybe 91%. Then increase it further. If you increase it too much, the coverage goes above 95% because every interval is very wide. Right? So there's some sweet point, right? Where the multiplier is not 2 standard errors, maybe 4 standard errors, at which I will hit 95%. In that case, I will report all my confidence intervals with 4 standard errors, beta hat plus or minus 4 SE. And that will capture all the variability in the whole machine learning search. Right? This is even better than the bound-for-only correction. You know bound-for-only correction? Bound-for-only correction is if you have several intervals, you want simultaneous at 95 at level 1 minus alpha, you slice the alpha to alpha over 5 for each, so that each one has only alpha over 5 error, so they add up to alpha if there's a 5 of them. That's bound-for-only correction. Here we cannot do a bound-for-only correction because we cannot even count how many things we're trying. How do you account for the search for the splits, right? So with this idea, of course, this idea will not work because we don't know the true F. That's what the bootstrap is. The bootstrap just says, use your data as your unknown F. The rationale is that as the sample size goes to infinity, this F hat is going to converge to F. Right? So if I think of this, now instead of drawing samples from this unknown F, I just store my F hat in the computer and I run my same simulation code on F hat. All right? I keep running it until I hit the sweet spot. Okay? And okay, you may ask, is this right? Well, I have one justification for you. So years ago in 1987, I wrote a paper in JASA where I tried to get confidence intervals, bootstrap confidence interval for the population mean. Okay, so we all know, so forget about multivariate here, just there's no X, just Y. So imagine you have IID observations from F with some mean and some variance. All right, we have a usual unbiased estimate of sigma squared. And the generic interval has this form, right? It's Y plus or minus some multiplier I call capital T times the standard error for the average, which is square root S divided by square root sample standard deviation by sample size. Now we all know from theory that if F is normal, the true T should be a T quantile, right? Okay. So we know that because of this, because of the central limit theorem, right? Even if the true F is not normal, it is approximately correct as n goes to infinity. The error is 1 over, or the big O of 1 over n, the coverage. So if you use this, you use a normal theory, called a normal theory multiplier, even on a non-normal population, all right? Asymptotically by the central limit theorem, it will converge to your correct coverage at the rate of 1 over n. What I did in 1987 is that, well, first of all, if F is known, you don't even need its asymptotic, right? You just do it by, you can get it, I say it's arbitrary precision because how many simulations you run. If F is unknown, now we're going to approximate F with F hat, right? So, and then we're going to draw from F hat. We don't really need to draw the data, but we just need to draw the sufficient statistics, which is a mean and standard deviation. So I put Y bar star and S star. The star refers to the bootstrap quantities. And I calculate the T statistic, right? And then I do this 10,000 times. And so I have 10,000 T statistics from my bootstrap loop. And I take the upper alpha quantile of it. So I sort my 10,000 bootstrap values of T, look at the quantile. And then I just replace capital T with this. All right. put it here. What I proved in 87 is I beat the central limit theorem. It's order 1 over n squared. See, because the bootstrapping, when you do the bootstrap, the only thing they make an error is your f hat is not exactly f. Everything else is the same algorithm. Here, the algorithm is very simple, just calculating the t statistic. In guide, the algorithm is the guide algorithm, right? I'm not using any Taylor approximation here. I'm not doing any approximation. The only approximation is f hat is approximating f. If I have f, I don't even have to use f hat, then I get it exactly right. It's not asymptotic, it's finite sample. Okay, so that's, I can't prove this theorem for guide, that's very complicated, right? But if you want to think there's any chance that this will work, it works fabulously here. In fact, it even beats the order rate of convergence. Okay. The reason why this is order 1 over n instead of 1 over square root n, in case you're wondering, is because I use a two-sided interval. If I use a one-sided interval, the skewness will come in, and then it's 1 over square root n. But if I use one-sided, my bootstrap method will still improve on that by order. Okay, so back to the guide method. I don't have time to talk about it. So this is basically what's happening, right? I have my data. This is my real data in my computer. Okay, I draw a bootstrap sample. So I do this 5,000 times. So my bootstrap sample looks like this. If you look at the right-hand side, it seems more sparse than the left-hand side. That's not because of a mistake, because they're over-sampled. Some points are sampled more than one. Some points are not sampled because I'm doing sampling with replacement, right? So here's a typical bootstrap sample. I grow this tree, and this tree gives me these partitions, right? So within each of these partitions, I have a beta hat. I carry these partitions, map it back to the real data, the same partition. Now I get my beta 0, or beta, just beta. Is beta hat. Right? So the idea is very simple. Yeah, I get different trees for every bootstrap, which is critical. You see, you cannot grow one tree and you bootstrap data from that tree. The tree topology has to change because you are trying to account for the variability in the search. If the tree never changes and you just bootstrap data from the terminal nodes, you are missing a huge chunk of uncertainty. Right? So this is one bootstrap tree. If I draw another bootstrap, it may not look like that. It may not have 3 terminals. Maybe have 4, maybe have 5, maybe have 2. It doesn't matter, right? Because each time I have to count how often all my intervals cover the estimates. If they all cover, I say I have one success. If one of them misses, I say I have 0. And then I tabulate over 5,000 simulations. And I want that average of ones and zeros to be 95%, whatever you want. So in my experience, and I've done simulations, a lot of simulations, this method works very well. I mean, it definitely improves the coverage compared to no adjustment. But the cost seems to be, it's about 4 times standard error, I would say, 4 to 5. So your intervals will be twice as wide. Okay, but you think about it, you have to pay a price, right? I mean, you are paying me to search for you across this very high dimensional space, right? And I mean, there are a lot of errors involving, you know, 21 instead of 21, maybe 22, maybe 23, right? So all these have to be included. The wonderful thing is maybe 4 is not too bad, not like 400. Okay. All right, so I'm well past your bedtime. Thank you very much for coming to these lectures. I enjoyed talking about it. I always enjoy talking about my work. If you happen to be interested in guide, you're welcome to go to my website. Lots of papers there. And I have software for 3 platforms, Linux, Macintosh, and Windows. The executable codes are all there. I have a 300-odd page manual, which I keep revising because I teach it every year. 1 year I teach the undergraduates, 1 year I teach the graduate students in Wisconsin. And if you have any questions, I'll be happy to answer them for you. I've stopped getting bug reports because I think the software is pretty, after 40 years, it is pretty stable. So, all right, thanks for coming. By the way, I know his name is Louis. What's your name?
Manuel. Manuel.
Manuel. Okay. Where are you from?
Austria.
Austria.
Yeah.
Oh, you know, there's a group of people from Austria, Germany, who write our package called Party Kit.
Okay.
Yeah. If you Google Party or Party Kit,
right,
they have an our version of some of these things. And I know a few of them that I know them quite well.
Okay.
Yeah, one of them is in a university in Austria, and the others are. They used to be a. Let me turn off this thing first. They used to be graduate students together when they were